Did you know that 95% of the universe is still unknown? Fabiola Gianotti, the Director General of CERN, has revealed this reality to us. The organisation is striving to change this percentage and broaden our mindset. Are you excited about exploring the ideas and history of CERN further? Let's dive in. That's exactly what we're going to do in this video. First, let's see what CERN is. CERN is the greatest organisation for research related to nuclear physics. It was founded in 1954 by 12 European countries and has grown to become a global leader in particle physics research. Its primary mission is to uncover the universe's fundamental structure by studying the smallest particles and the forces that govern their interactions. Moreover, CERN operates through a complex organisational structure in which 23 member states and numerous associate and observer countries contribute to its research efforts. It is governed by the CERN Council, which comprises representatives from each member state. The organisation's funding primarily comes from its member states, with additional contributions from associate members and other partnerships. CERN has a significant history dating back to World War II. The concept of a collaborative European research organisation emerged in the early 1950s, driven by the need for peace and the desire to advance scientific knowledge. On September 29, 1954, CERN was officially established by 12 founding member countries. Its initial focus was on nuclear research, reflecting the scientific priorities of the time. Early experiments used particle accelerators, such as the synchrocyclotron, which became operational in 1957. It was soon followed by the proton synchrotron, which began operating in 1959 and allowed scientists to explore higher energy physics. CERN's research scope expanded significantly over the following decades. The construction of the superproton synchrotron in the 1970s marked a significant milestone that enabled groundbreaking experiments. In this time frame, the intersecting storage rings, the world's first Hadron Collider, operated from 1971 to 1984. In the 1980s, CERN embarked on one of its most ambitious projects, constructing the Large Electron Positron Collider, LEP. LEP played a crucial role in testing the Standard Model and provided precise measurements of fundamental particles. LEP's legacy paved the way for CERN's most famous and powerful accelerator, the Large Hadron Collider. The LHC, which became operational in 2008, is a 27-kilometre ring underground on the border between Switzerland and France. It accelerates protons to near light speed and collides them, allowing scientists to observe and study the fundamental particles and forces of the universe. The LHC is home to several significant experiments, including ATLAS, CMS, ALICE, and LHCb, each designed to investigate different aspects of particle physics. Throughout its history, CERN has been a hub of innovation in particle physics, technology, and computing. It has also contributed to advances in medical imaging, data processing, and materials science, demonstrating its far-reaching impact beyond fundamental research. Now, here's the interesting thing about CERN. Its primary goal is to understand the universe's fundamental structure by investigating the smallest particles and the forces influencing their behaviour. By studying particles such as quarks, leptons, and bosons, and their interactions through fundamental forces like electromagnetism, strong and weak nuclear forces, and gravity, CERN aims to unravel the mysteries of the universe at the most basic level. This involves probing dark energy and studying the universe that was created after the Big Bang. Moreover, particle physics studies the smallest known particles and the fundamental forces acting upon them. CERN's particle accelerators, like the Large Hadron Collider, collide particles with immense high energies. You'll be surprised if I tell you about these collisions, because the high energies create scenes similar to those after the Big Bang. Those collisions allow scientists to observe rare and fleeting phenomena while evaluating the properties and behaviours of fundamental particles. High energy physics involves studying particles at extremely high energy levels, enabling the exploration of phenomena that can't be observed at lower energies. The LHC is central to this research as it has the ability to accelerate particles to near light speed and creates collisions at unprecedented energies. High-energy physics experiments at CERN aim to discover new particles, understand the nature of forces at small scales, and investigate the potential existence of extra dimensions and other theoretical concepts beyond the standard model. It's incredible, isn't it? Before I discuss other unique details about CERN, let's subscribe to the channel. This way, you won't miss an update and can continue the journey of cosmic exploration. Now, let's move toward another fantastic concept: quantum mechanics. It deals with how particles behave at the tiniest scales, another crucial area of research at CERN. Understanding quantum phenomena is essential for explaining how particles interact and combine to form matter. CERN's experiments observed that the principles of quantum mechanics to study particle behavior, quantum field theories, and the underlying symmetry principles that govern particle interactions. This research has profound implications for fundamental science and practical applications, influencing fields such as quantum computing and information technology. Let's see the current projects at CERN. CERN continues to lead the field of particle physics through several high-profile projects aimed at expanding our understanding of the universe. The key projects include upgrading the Large Hadron Collider, developing the Future Circular Collider, and various ongoing experiments that observe dark matter, antimatter, and the conditions of the early universe. The Large Hadron Collider is undergoing significant upgrades to enhance its capabilities for future experiments. This upgrade, known as the High Luminosity Upgrade, aims to boost the collider's luminosity, which refers to the rate at which particle collisions occur. Higher luminosity will enable scientists to collect more data, improving the precision of measurements and increasing the chances of observing rare phenomena. The upgrade involves several technical advancements, including developing more powerful superconducting magnets to focus better particle beams, advanced cryogenics to maintain the necessary low temperatures, and upgraded detectors to handle the higher collision rates. These improvements will allow the LHC to operate nearly twice its original design luminosity, significantly boosting its discovery potential. Looking further ahead, CERN is planning the Future Circular Collider, the next generation particle collider designed to push the boundaries of particle physics even further. The FCC aims to be the successor to the LHC, with a circumference of up to 100 kilometers, making it almost 4 times larger than the LHC. This project envisions achieving collision energies of up to 100 TeV, tera-electron volts, compared to the LHC's current maximum of 14 TeV. It's amazing. The FCC is expected to provide unprecedented insights into the forces of the universe. It would allow for exploring phenomena currently beyond the reaches of existing colliders, such as detailed studies of the Higgs boson, the potential discovery of new particles, and investigations into dark matter and extra dimensions. The development of the FCC is still in the conceptual and design phase, with ongoing international collaboration to address the significant technical and financial challenges associated with such a large-scale project. CERN's ongoing experiments continue to explore some of the most profound questions in physics. Amongst these is the research into dark matter. Experiments like those conducted with the Alpha Magnetic Spectrometer in the International Space Station are critical in searching for dark matter particles and studying cosmic rays to understand the composition and origins of the universe. The AMS experiment, operational since 2011, aims to detect antimatter and dark matter by analysing high-energy particles from outer space. By studying the properties of these particles, scientists hope to uncover clues about the nature of dark matter and the imbalance between matter and antimatter in the universe. The AMS has already provided valuable data, including measurements of cosmic ray positrons and antiprotons, which have implications for dark matter theories. Another focus area is the study of the early universe, precisely the conditions that existed shortly after the Big Bang. Experiments at CERN, such as those conducted by the ALICE, a Large Ion Collider experiment collaboration, recreate the extreme conditions of the early universe by colliding heavy ions at high energies. These collisions produce plasma, a state of matter that came into being after the Big Bang. It allows scientists to study its properties and understand the universe's evolution. Now, let's explore challenges faced by CERN. The main concern is the financial investment required to build and maintain advanced research facilities. Projects like the Large Hadron Collider and the proposed future Circular Collider involve enormous costs, often billions of dollars. These expenses cover the construction of complex infrastructures, developing cutting-edge technologies, and operating and maintaining existing facilities. Securing sufficient funding for these projects requires ongoing support from member states, associate members, and other international partners. It can be challenging, especially during economic uncertainty or competing priorities. The high costs associated with these projects also demand efficient resource management to ensure that funds are used effectively and that projects remain on schedule and within budget. CERN also faces ethical and safety challenges related to its high-energy experiments. Public concerns about the safety of particle collisions, such as those conducted in the LHC, have been a topic of debate. Some worry about the potential risks of creating new particles or states of matter despite extensive scientific evidence and safety assessments demonstrating that these experiments are safe. To address these concerns, CERN must maintain transparency and openly communicate with the public. This involves clearly explaining the scientific objectives and safety measures for high-energy experiments. Independent safety reviews and assessments by external experts are also needed to ensure credibility. Now, let's recall the crucial pointers from today's video. CERN is a leading scientific research institution that was established in 1954. Its most famous facility is the Large Hadron Collider, known for discovering the Higgs boson in 2012. Current projects include upgrading the LHC to increase collision rates and planning the future Circular Collider for next-generation research. CERN also experiments on dark matter, antimatter, and the early universe. Every path has challenges, but every challenge creates a path for future success. CERN really belongs to this fact. The organisation is working deliberately to understand the phenomena of the universe, and everyone should strive for knowledge related to it. That's all for today. Share your thoughts and questions in the comments section.